Hi everyone, I'm finally getting a chance to make this video on 5-3 part 2. So first, to be clear, we've done absolute extrema and the candidates test, and this is on your quiz on Monday. This part 2 that I'm going to talk about is not on your quiz on Monday. Let's begin by just looking very quickly at this table. I think I was able to talk about the table in one class but not in the other, but I just am going to go over it very briefly. You can just study it and read it on your own, and it will make sense after we do the examples. We have various tests that we can use looking at f prime and f double prime and then making conclusions about f. So for example, if f prime is greater than 0, that means slopes are positive, so the function is increasing. If f prime is less than 0, then slopes are negative, my function is decreasing. Concavity test is about f double prime. So if you have concave up, that means your slopes are actually, so this is f, the slopes, which are f prime, are going to be increasing, because if you think about it, your slopes, maybe -4, -3, -2, -1, 0, 1, 2, 3, 4. So slopes are increasing. That means f double prime will be greater than 0. That gives us concave up. Similarly, if f double prime is less than 0, we have concave down for f, right? So we're looking at what f double prime is doing, and we're making a conclusion about f. So down further on the table, we can also look at relative maxima or minima. We already know that these occur whenever you have a critical point. So whenever the derivative is 0 or does not exist, we have a possible local extrema, right? Possible extrema, local. And the way we can decide if we really do have a local max or min is by two possible tests. We can either do what's called the second derivative test or the first derivative test. The second derivative test says that if you are at a critical point and you find that at that point f double prime is greater than 0, then you are sure that you have a relative relative minimum there. So in other words, you're at a critical point like this, you've figured out that f prime is equal to 0 at that point, and you're going to check now f double prime, and if you find that it's greater than 0, then the only way that could happen is if you're at the bottom of a U shape like that, so you're at a relative minimum. Similarly, if f double prime is less than 0, then your graph must be like this. You are at the top of a hill. So if you're at a critical point and f double prime at that point is less than 0, then you have a relative max. Sorry about the typos. Now, if f double prime at the critical point is either 0 or does not exist, right? So it's neither positive like here, nor is it negative. It's 0 or it doesn't exist. Then you can't use the second derivative test to decide if you're at a relative max or min. You have to resort to what we call the first derivative test, and that's the one where you go to the critical point, say that's C, and you're going to look at the sign of f prime on both sides of C. So if you come here and you figure out that the sign of f prime on this side is positive and this side is negative, so the sign changed at that critical point and went from positive to negative, then you must be at a relative max, because slopes went from positive to negative, right? If f prime goes from negative to positive, then you must be at a relative min. And if f prime doesn't change sign, so it's at a critical point, but f prime doesn't change sign, then you have neither a max or a min, and that's a situation that looks like this. So we've got like a 0 for our horizontal tangent right at that point, but the graph of f is increasing on both sides of f. Okay, and the last thing we want to mention is called points of inflection. Points of inflection are where concavity changes. So we talked in class about concave up being like this and concave down being like that. In terms of calculus, concave up means the tangent lines are below the curve. Concave down means the tangent lines are above the curve, right? So point of inflection is the place where concavity changes, like right there. So this piece right here is concave down, and then right there I change to concave up, okay? So that means that this point will be called a point of inflection. And the way we recognize points of inflection using algebra is we find f double prime, we set it equal to 0, and then we make a sign chart for f double prime, and we see whether it changes sign. So say C is where f double prime equals 0. We're going to look on both sides and see what happened. Did it change sign? If f double prime changes sign, like you can see here, you know, f double prime here would be negative, and then on this stretch right here, because I'm concave up, f double prime must have become positive. So if f double prime changes sign, then we're at a point of inflection. Okay, so our first example is, here's a function f of x, and we are trying to find in part A the intervals of increase and decrease. So we're going to take a derivative, f prime, that's 3x squared minus 6x minus 9. We're going to factor that because we're going to need to do that to figure out the sign. And so we get 3 times x minus minus 3, yes, and x plus 1. Okay, so now to figure out the sign, I am going to make my number line. I'm going to realize that when x minus 3 equals 0, x is equal to 3, right? So that I got by setting this factor equal to 0. That's going to be a number that I write on my number line. That's going to be a critical point where f prime is 0. And then I do the same thing with x plus 1 equals 0. I get x equals negative 1. That's also a critical point. So I'll go ahead and put that on the number line also. And now that divides up my number line into intervals, right? I can think of it as I have an interval here from negative infinity to negative 1. And then I have an interval here from negative 1 to 3. And then I also have an interval from positive 3 to infinity. So these critical points divide your number line into intervals. And now we need to figure out the sign of f prime on each of those intervals. So we can just do that by simply doing test points, and we'll figure out that f prime is positive here. It's also going to be positive here, and it's going to be negative here. If you like the way we did it with position and velocity problems, thinking of the sign of these two factors and then the sign of the product, you can do it that way as well. So now that we know the sign of f prime, it's really easy to understand where f is increasing or decreasing, because f will simply be increasing whenever f prime is positive. It will be decreasing when f prime is negative, and it will be increasing again here because f prime is positive. So my intervals of increase, let's write the answer up here. Intervals of increase are going to be negative infinity to negative 1 and 3 to infinity. And my interval of decrease is going to be from negative 1 to negative 3. Okay, so for part B now, we are going to look at local minima and maxima. I want to show you two ways to do that. First, I'm going to use the second derivative test. And for that, I'm going to take these critical points that I've just found here. That means set f prime equal to 0 or f prime does not exist. Figure out where that happens. Find all the critical points. And then find the second derivative at those critical points. So in this case, I need f double prime of 3 and f double prime of negative 1. So f double prime of 3, we need f double prime of x first. So we'll just find that taking one more derivative there, and we get 6x minus 6. And now f double prime of 3 will be 6 times 3 minus 6, or 12. And f double prime of negative 1 is negative 6 minus 6, which is negative 12. So that means that at x is equal to 3, I have a graph that has to have a horizontal tangent line because f prime is 0, but I also have to be concave up. And the only way that can happen is if this is a minimum. And similarly here, since f double prime is less than 0, then it's a maximum. So that means my minimum is at 3 and my maximum is at -1. And now I need to find f of 3 and f of -1 to write my final answer. So f of 3 is 27 minus 27 minus another 27 plus 4. So I think that's equal to -23. And f of -1 is -1 minus 3 plus 9 plus 4, which I think is +9. So f of 3 equals -23. This is my local minimum, and f of -1 is equal to 9 is my local maximum. Now, in this problem, when we did f double prime of the critical point, it worked out to a number. We didn't get 0 and we didn't get does not exist. If we had got f prime double prime equals 0 or does not exist, we would have had to do what's called the first derivative test, right? And we've actually done the first derivative test right here, because when you find the sign of f prime on two sides of that critical point, you are really performing the first derivative test. And the first derivative test would say f prime went from positive to negative here. So that means this right here, this critical point must have been a max. And f prime went from negative to positive here. So this critical point must have been a local min. So that's how you could apply the first derivative test as well to find those places, those x values of max and min. And then of course you'd have to find f of the values, just like we did here to get our y values. Okay, last piece of the puzzle is intervals of concavity, and for that we have to look at the sign of f double prime. So we're going to take a look at f double prime more closely. That's 6x minus 6. So again, set it equal to 0, figure out where that happens. That happens at x equals 1, and now analyze the sign of f double prime on both sides of 1. So good to notice that this can also be written as 6 times x minus 1, and that might make it clearer that we have positive values here and negative values here. So, and also, by the way, you can test points if you prefer. So now we can look at it as intervals. So this interval right here is 1 to infinity, and so on 1 to infinity, I'm concave up. The function f is concave up. And this other interval right here is negative infinity to 1. And for that stretch, I am concave down. F is concave down. And to be complete, we really should say because f double prime is less than 0. And here we were concave up because f double prime is greater than 0. Okay, next example is right here. We have a rational function, and we're doing the same things that we just did in parts A, B, and C. So the first thing we're doing is finding the intervals of increase and decrease. So we'll find f prime, and we'll analyze the sign of f prime. So to find f prime, you can use either product or quotient rule. I'll choose to use quotient rule right here. So I'm doing low d high minus high d low over low squared. I'm then cleaning up my numerator. So 3x cubed minus x cubed gives me 2x cubed minus 2. Be careful with this sign, distribute it properly. And so I have an equation right here for f prime. And I have to now think about the sign of that equation. So first of all, find where it's equal to 0. So that's a critical point. So let's go off here and talk about critical points. So we'll set this equation to 0, and we'll think about when that happens. So when you have a situation like this with the denominator set to 0, just think about it as 0 over 1 and cross multiply. So we get 2x cubed minus 2 is equal to 0. X cubed is equal to 1. And so x is equal to 1 also. Okay, so remember that when we're finding critical points, we just found one by setting f prime equal to 0. You also always need to think about f prime being does not exist, right? So we have to look at the domain of f prime. And so when you look at this f prime equation right here, we realize that x is equal to 0 is an excluded value. It's because of the denominator. So you might be wondering, is that a critical point because f prime does not exist at x is equal to 0? Well, we don't have to worry about it because if you look at f, right, f also has an excluded value at 0. X equals 0 is not in the domain of f, so it is not necessary to include it as a critical point. Okay, so now we have a sign chart that we can draw, so let's go ahead and do that. To look at the sign of f prime, so I put 1, this critical point, on my sign chart, and I test points. I figure out that f prime is positive here and negative here just by plugging back into that equation. And so that means that f is decreasing here and increasing here. So I will say it properly as f is increasing on negative 1, positive 1 to infinity, because f prime is positive on that stretch, and f is decreasing on negative infinity to 1 because f prime there is negative. Okay, my next piece is the local minimum. That was part B. So for that, I'm going to I've actually already done the first derivative test. What we did here with the sign chart was the first derivative test. I found the critical points and I found the sign of f prime on both sides of the critical point. And so I can conclude that since I must be decreasing and then increasing, this point right here at x equals 1 must be a local minimum. So the way we write that is we're going to come over here and first of all find f of 1, because we're going to need that. 1 plus 2 divided by 1 is equal to 3. And then we can say f of 1 equals 3 is a local minimum because f prime changes from negative to positive. That's what we have to say for a justification. Okay, in part C, we're asked to look at concavity. So we start with f prime of x, which we have, and we are going to differentiate one more time to get f double prime of x, because that's what's going to drive concavity. So we do low d high minus high d low over low squared. And so we're going to get 6x to the 4th minus 4x to the 4th plus 4x over x to the 4th, which simplifies to 2x to the 4th plus 4x over x to the 4th. Now this is f double prime, and we need to think about the sign of f double prime. So we'll first set it equal to 0 and find where that happens. So if you set this equal to 0, once again, just by cross multiply, you realize that all we have to do is set the top equal to 0 and solve that. Pull out 2x, and we have x squared plus 2 is equal to 0. Now this is interesting. Have to be careful here. We'll have two solutions from here. One is by setting 2x equals 0, so we get x equals 0. The other is by setting x cubed plus 2 equals 0, x cubed equals negative 2. And this does have a solution because negative numbers do have cube roots. So this is going to come out to be, on your calculator, negative 1.414. The square root of 2 is about 1.414. And so when we do our f double prime number line, we're going to have x is equal to 0 and x is equal to negative 1.414. And we now need to check test points. So we're looking at this equation right here and putting in points, and you're going to find when you do that, that we have f prime will be positive here, and negative here. So that means the function will be concave up here, and concave down here. In terms of intervals, we're saying that on this stretch from negative infinity to negative 1.414, we're concave up. And we're also concave up once we get past 0. So 0 to infinity is also concave up. And then concave down interval is from negative 1.414 to 0. And this is because f double prime is less than 0. And here it's because f double prime is greater than 0. Okay, this function also has a point of inflection. In fact, it has two of them. Points of inflection at x equals negative 1.414 and x equals 0 because f double prime changes sign. So we're talking, remember, about f. F has points of inflection because f double prime changes sign. Okay, let's talk about this problem. F prime of x is going to be first times the derivative of the second plus the second times the derivative of the first. Product rule there. And this derivative, I use the chain rule. So cleaning this up, negative 2x squared e to the negative x squared plus e to the negative x squared. Pull out an e to the negative x squared. And then we have a factor of 1 from that and minus 2x squared from that. Okay, so now let's find the critical points. So the critical points will be when f prime is equal to 0. So set the f prime equation equal to 0. Realize that this is an exponential which will never touch the x-axis. It'll never be 0. So all I have to do is this piece. So then negative 2x squared equals negative 1, x squared equals 1/2, x equals plus or minus the square root of 1/2, which is plus or minus 0.7071 roughly as a decimal. So let's make a sign chart. Just come over here and put those two numbers on the chart. And then pick points to test f prime in the different intervals. So let's see, we have 3 intervals here, 1, 2, and 3. So let's pick 1, which is in this interval, and f prime, let's think about f prime, that's this equation now. So f prime of 1 would be e to the negative 1 times 1 minus 2 times 1 squared. So e to the negative 1 is just 1 over e. That's a positive number still, and then this piece is negative. So I'm negative over here. Let's check f prime of 0. That would be a nice number in the middle interval. So that's e to the 0 times 1 minus 0. So this e to the 0 is 1, and this is 1, so I'm positive here. And then let's check f prime of negative 1. It will be e to the negative, right? Negative, and then x squared is in there, so this will still be e to the negative 1, or 1 over e. And then I get 1 minus 2 times negative 1, the whole thing squared, which will be positive 1. So this f prime of negative 1 and f prime of 1 will be the same, which maybe you could also have seen by realizing that this guy is an even function. If you understand that, great. If you don't, it's not a big deal. But we realize now that this is negative on this side. F prime of negative 1 is also negative, so we're negative here. So function f is decreasing, increasing, and decreasing. And then, of course, you can write that as intervals. So we're decreasing on negative infinity to negative 0.7071. We're increasing between negative 0.7071 and positive 0.7071. And we are increasing again once we get past positive 7071. Okay, in terms of local minima and maxima for this problem, let's see, we have our first derivative test already here, right? We know the sign of f prime on the two sides of these critical points, And so we can tell, we can always resort to that second derivative test, but that would be just a waste of time here because we've already got the first derivative test all ready to go. And we can say that this point right here has to be a local minimum because f prime went from negative to positive, and this point right here has to be a local maximum because f prime went from positive to negative. So we can say that here for part B, local min at 1 over rad, negative 1 over rad 2, local max is at 1 over rad 2. That's the negative 0.7071, and this is the positive 7071. So now we have to do f of negative 1 over rad 2 because we need the y value. So it'll be negative 1 over rad 2 e to the negative 1/2, and this guy will be positive 1 over rad 2 e to the negative 1/2 as well. And you can verify that for yourself. Those are our absolute, local, not absolute, maxima. And okay, yay, we are on our last problem. So it's a trig problem. I wanted to make sure I do one of these. So I'll find my derivative just as usual. That'll be cosine x minus sine x. To find critical points, I'll notice that that derivative is defined everywhere. So all I have to worry about is f prime equals 0. I'll do that, set it equal to 0, and try to solve that equation. So this means negative sine x equals negative cosine x. Divide both sides by negative cosine x to get that tangent x is equal to 1. So x must be equal to either pi over 4 or 5 pi over 4. That's from the unit circle and restricting myself to this domain. So now I can draw my sine chart. I'm going to go from 0 to 2 pi and think about pi over 4 and 5 pi over 4 as my critical points and figure out the sign of f prime. Choose values here. I can choose 0 for this interval here, and then I can choose maybe pi over 2 for this interval here, and I can choose 2 pi for this interval because 0 and 2 pi are included right in the domain. So I'm okay choosing those, and so I can just figure out that f prime will be here, it'll be cosine of 0, that's 1, minus sine of 0, that's 0. Here it's positive. Here it'll be, I can take pi over 2 as my spot and go cosine pi over 2 is 0, minus sine pi over 2 is 1, so here it's negative. And here when you pick 2 pi, you'll find that it's positive. So f is increasing, decreasing, increasing, and then you can write that in interval notation like we did before. Now, as far as maxima and minima, notice that here we're set up to do the first derivative test because we already have the sign of f prime around the critical points. So this must be a maximum, a local maximum, because f prime is doing this. It's going positive and then negative, so that must be a local maximum. This right here must be a local minimum because f prime is changing from negative to positive, so this is a local min. And so all I have to say for part B is local max at, I just have to find f of pi over 4, and then local min, I just have to find f of 5 pi over 4. So we can just go back into our function, sine x plus cosine x. So at pi over 4, that becomes rad 2 over 2 plus rad 2 over 2, which is 2 times rad 2 over 2. That's simply rad 2. And then you do the same thing here for 5 pi over 4, and both of these will be negative. And so you get negative rad 2 as your local min. So the last piece of this question is our concavity and points of inflection. So as usual, we're going to find f double prime of x. So f double prime of x, in this case, we take f prime, differentiate again to get this. And now we want to find where that's equal to 0. So let's do that. Set f double prime x equals 0. Solve for this. So we're going to get here negative sine x equals cosine x. So now when we divide by cosine x, we'll get negative tangent x is equal to 1. or tangent x is equal to -1. So then x would be equal to, in this case, 3 pi over 4 and 7 pi over 4, right? So these are on the unit circle, tangent is negative here and here, -1. So 3 pi over 4 and 7 pi over 4. Okay, so let me show you how I would set up this sign chart for f double prime to make sure we don't make a mistake. I would go 0, 2 pi, and then I would just kind of count up in pi over 4s, because I know I'm going to have to position 3 pi over 4 and 7 pi over 4 on this number line. So I'm going to think, I can count up by pi over 4. 0, pi over 4, pi over 2, 3 pi over 4, 4 pi over 4, which is pi, 5 pi over 4, 6 pi over 4, which is 3 pi over 2, 7 pi over 4, and then 8 pi over 4, which is 2 pi, right? So just think like that so you get this positioned properly. We actually don't need pi on our number line. We only need 3 pi over 4 and 7 pi over 4. So we can think, well, 3 pi over 4 is there and 7 pi over 4 is here. And so when you're choosing your points, you won't make a mistake, because you got to choose a point that's in the interval. So for this interval, you might choose 0, or you might choose pi over 2, which is also in this interval right here. Then for this middle interval, you might choose 4 pi over 4, or pi. That's a good convenient number. And then here you might choose 2 pi would be a good convenient number there. So you do that and you figure out the sign of f double prime. So let's see, if I do 0, then f double prime of 0 minus sine 0 minus cosine 0, and this will be -1, so we're negative here. F double prime of pi, right, that's this. That would be equal to minus sine pi minus cosine pi. So that's equal to sine of pi is 0 and cosine pi is -1. So that big negative of -1, that's +1. So it's positive here. And then f double prime, don't make any assumptions. It's not always minus, plus, minus, or anything like that. You have to pick a point and check. So we'll check f double prime of 2 pi minus sine 2 pi minus cosine 2 pi. Sine 2 pi is 0, cosine 2 pi is 1, so this is -1, so it is negative here. So that's f double prime. So we're going to make our conclusions about f as concave down, concave up, and concave down. And we have points of inflection at 3 pi over 4 and 7 pi over 4, because f double prime changes sign at those x values. Okay, we did it. I know that was long and there was a lot there. We'll have a lot of practice on the homework and in the next couple of classes to digest it all. But I just wanted to give you a few good examples of all these things that we need to learn. And I hope that that was clear, and we'll talk in class.